Module 7, Chapter 4.2, More on Graphs of Rational Functions. In the last section, we mentioned the vertical and horizontal asymptotes and defined them as lines the graph would never or usually never cross. Actually, the graph will never cross the vertical asymptote, but it could cross the horizontal and/or oblique asymptote. Now we are ready to give a more formal definition of each. For the rational function, f of x equals p of x over q of x, written in lowest terms, if f of x, the absolute value of f of x, approaches infinity as x approaches a, then the line x equals a is a vertical asymptote. What that means is if the function approaches infinity, the absolute value means it could approach it in the positive direction or in the negative direction. As x approaches some number, then that number is the location of the vertical asymptote. If f of x approaches a as x approaches positive or negative infinity, then the line y equals a is a horizontal asymptote. What that means is if the function's value get closer and closer to a number as x gets larger or smaller, then that is the location of the horizontal asymptote. So let's go through and find a couple. To find the vertical asymptote of a rational function defined by a rational expression in lowest terms, use the following procedure. To find the vertical asymptote, set the denominator equal to 0 and solve for x. If a is a 0 of the denominator, but not the numerator, then the line x equals a is a vertical asymptote. To find the horizontal asymptotes of a rational function defined by a rational expression in lowest terms, we're going to use the following procedure. If the numerator has lower degree than the denominator, then there is a horizontal asymptote at y equals 0, or the x-axis. If the numerator and the denominator have the same degree, then the line y equals a sub n over b sub n is the horizontal asymptote, remembering that a sub n is the coefficient of x to the highest power in the numerator, and b sub n is the coefficient of x to the highest power in the denominator. To find oblique asymptotes of a rational function defined by a rational expression in lowest terms, use the following procedure. If the numerator is of degree exactly 1 greater than the denominator, there may be an oblique asymptote. To find it, divide the numerator by the denominator, disregard any remainder, and set the rest of the quotient equal to y to get the equation of the asymptote. And that probably doesn't make a lot of sense right now, but we'll do an example to show you what they're talking about. A couple of notes. The graph of a rational function may have more than one vertical asymptote, but it cannot intersect any of them. The graph may have only one other non-vertical asymptote, and it may intersect it, which means there may be a horizontal asymptote or there may be an oblique asymptote, but there cannot be both. Okay, let's try one. Find the asymptotes of the graph f of x equals x plus 1 over 2x squared plus 5x minus 3. Now the first thing we need to notice is this rational function needs to be in reduced form. So let's go through and let's make sure that this will not reduce. If we factor the bottom, 2x and x, 3 and 1, we know that 3 has to be different signs, plus 3 minus 1. We don't have any of the same factors in top and bottom, so it's not going to reduce. So, to find the vertical asymptote, we say, well, we're going to take the denominator and set it equal to 0. So we would have 2x minus 1 times x plus 3 equals 0. Set each of these equal to 0. 2x minus 1 equals 0. X plus 3 equals 0. That would give us x is 1/2, and that would give us x equals negative 3. So we're going to have two vertical asymptotes. In terms of the horizontal asymptote, if the degree of the numerator is less than the degree of the denominator, which remember, degree is the highest power. So this is degree 1, this is degree 2. So the horizontal asymptote, if the numerator degree is less than the denominator degree, is y equals 0. Okay, let's try another one. Find the asymptotes of the graph f of x equals 2x plus 1 over x minus 3. Well, to find the vertical asymptotes, you set your denominator equal to 0, plus 3 plus 3. So our vertical asymptote would be the line x equals 3. The horizontal asymptote, because the numerator and the denominator have the same degree, then we use leading coefficients. Leading coefficient of the numerator is 2. Leading coefficient of the denominator is 1. So we say that our horizontal asymptote is the equation y equals 2. Now, what about this one? Identify the asymptotes from the graph. Well, if you'll notice, the graph never crosses this line right here. So that means that the vertical asymptote is the line x equals 1. Now you notice this graph goes out this way and this graph comes this way, and it doesn't cross that, which means there's a horizontal asymptote of y equals 1. Let f of x equals p of x over q of x define a rational expression in lowest term. To sketch its graph, follow these steps. First thing, find all asymptotes. So we're going to find the vertical asymptote, then see if there's a horizontal asymptote or oblique asymptote. Then we're going to find the x and y intercepts. Remember, to find the x-intercept, you set it equal to 0. To find the y-intercept, you let x be 0. Then you determine whether the graph will intersect the non-vertical asymptote by solving f of x equals k, where y equals k is the horizontal asymptote, or y equals mx plus b is the equation of the oblique asymptote. Then we're just going to plot a few selected points as necessary. Choose a couple in each interval. Choose an x value between the vertical asymptotes and the x-intercepts. And then complete the sketch, which we can do a lot of these on our calculator to make sure that we're doing everything okay. Now remember, a comprehensive graph of a rational function will exhibit these features. It needs to show all of your intercepts, location of your asymptotes, and the point at which the graph crosses its non-vertical asymptote, if there is one. And it needs to show enough of the graph to exhibit the correct end behavior. So, you ready to graph one? So, f of x equals x plus 1 over 2x squared plus 5x minus 3. To find the vertical asymptote, well, actually, we're going to go through here and graph this and make sure it's in reduced form first. Okay, vertical asymptotes, as we found earlier, were 1/2 and negative 3. Because the numerator degree is less than the denominator degree, then the horizontal asymptote is going to be the x-axis, or just y equals 0. So we've got equals 1/2, which would be right through here. We've got x equals -3, which is going to be, I know that's probably hard to see, right through here. We've got a horizontal asymptote of y equals 0, which is right through there. And then we want to see if the graph will cross the horizontal asymptote. So what we're going to do is take the original function and set it equal to the y equal number, which we said was 0. Well, if we multiply both sides by 2x squared plus 5x minus 3, we get x plus 1 equals 0, which means it's going to cross this thing at x equals -1. So that one's on our graph. Because we set it equal to 0, that's also our x-intercept. Now, y-intercept, we're going to let x be 0. So we'd get 0 plus 1 over 2 times 0 squared plus 5 times 0 minus 3, which is 1 over -3. So the y-intercept would be -1/3. Okay, now we need just a few more points. So let's pick something back here. Let's pick x as -2. Well, if we let x be -2, that'd give us -2 plus 1, which is -1. That would give us -2 squared, which is 4. 2 times 4 is 8. -2 times 5 would be -10 minus 3. So that would be -1 over -5, or 1/5. So if x is -2, we'd get 1/5, which would be somewhere right in there. Let's pick something back here. Let's pick x as -4. That'd be -4 plus 1 is -3 on the top. That would be 2 times -4 squared minus 20 minus 3. Well, -4 squared is 16 times 2. So 32 minus 20 is 12, minus 3 is 9. So that would be -3 over 9, which would be -1/3. So if x is -4, we'd get -1/3. So what we're assuming here is that this graph comes down this way. It crosses, and then it gets close. Whoops. So what we're assuming is that this graph will come down like this. It's going to cross over through here and then get closer and closer here. Now what happens over here? You know, we'd have to pick a few more points in here. Same thing over here. If we pick x as 1, we'd get 1 plus 1 is 2. 2 times 1 would be 2. 2 plus 5 is 7. 7 minus 3 would be 4. So if x is 1, we'd get y is 1/2. So that's somewhere right in there. Remember, it's not going to cross anywhere out here. So it's probably going to look like this. Down here, it's not going to cross anymore, which means it's going to look like that. So if we wanted to check that one on our calculator, so we are going to enter x plus 1 in the top divided by 2x squared plus 5x minus 3 in the bottom. Graph that. You know, it doesn't show them all, but this one takes off down here. This one is in between here, and this one is this one. If we wanted to zoom in just a little bit, let's see if that would help us get a better picture. That's not going to, I mean, that gives us a little bit to the left. But anyway, so I think we're pretty good on our graph. Okay, let's do another one. F of x equals 2x plus 1 over x minus 3. First thing we're going to do is find our vertical asymptote. Take your denominator, set it equal to 0, and we get x equals 3. 1, 2, 3. So our vertical asymptote's taken off through there. Horizontal asymptote. Well, because the degree of the numerator are the same, degree 1, degree 1, then the horizontal asymptote is the 2 over the 1. So it would be y is equal to 2, which is going to be this little vertical line, horizontal line right there. Then we want to ask ourselves, will it cross the horizontal asymptote? Well, let's set it equal to 2. So we get 2x plus 1 over x minus 3 equals 2. Multiply both sides by x minus 3. So we get 2x plus 1 equals 2x minus 6. Subtracting 2x, we get 1 is negative 6. That has no solution, so it does not intersect that horizontal asymptote. To find your intercept, to find the x-intercept, we're going to set it equal to 0. Multiplying both sides by x minus 3, we get 2x plus 1 equals 0, so x would be negative 1/2, which means that is this point right here. To find the y-intercept, we plug in x is 0, which would give us 0 plus 1 is 1, over 0 minus 3 is negative 3. So if x is 0, y would be negative 1/3, which would be down here. So because it doesn't cross any of these, what we can assume is that it's going to come through here, cut through those lines, and then come and get closer and closer to that one. Now over here, let's just pick up a couple of points. If we pick x as 5, we'd get 2 times 5 is 10 plus 1 is 11. 5 minus 3 is 2, which would give us 5.5. So if x is 5, y would be 5.5. 1, 2, 3, 4, 5.5. Which means up here the graph is going to get closer and closer to the vertical asymptote. It's going to get closer and closer to the horizontal asymptote, so our graph would look something like this. Okay? Vertical asymptote, set the denominator equal to 0, which we get x is 2. Horizontal asymptote, well, in the case where the degree of the numerator is only 1 more than the degree of the denominator, we say there's not a horizontal, but there may be an oblique. So the way you check this is you divide. So if we divide x squared plus 1 divided by x minus 2. Now this is our perfect synthetic division that says if you're dividing by a binomial x minus 2, then we can do synthetic by 2. So we get 1x to the second, 0x plus 1. Drop that. So 1 times 2 is 2. And that would be a 4, and that would be a 5. So in this case, you always throw out your remainder. So this would be x plus 2, which says our oblique asymptote is y equals x plus 2. So if we were to sketch these on here, vertical asymptote x equals 2. So that's going to take off right through here. Oblique asymptote y equals x plus 2. Well, that has a y-intercept of 2. Slope is 1. So this is this little line right here. Now remember, these are not technically part of the graph, but we're going to put them on there just so we'll know where our graph is going. Then we want to ask ourselves, will the graph cross the oblique asymptote? Well, in that case, what we do is we take our original function and set it equal to this, what we just found for the oblique asymptote. Now, multiplying both sides by x minus 2, we get x squared plus 1 equals x plus 2, x minus 2, or x squared plus 1 equals x squared plus minus 4. Well, subtracting x squared gives us 1 is negative 4, which means there's no solution, which means it does not cross this oblique asymptote. So now we want to find our intercepts. Well, to find the x-intercept, we set our function equal to 0, which would give us x squared plus 1 equals 0. That has no solution because x squared equals negative 1, so that means it doesn't cross the x-axis. The y-intercept, we're going to let x be 0, so we get 0 squared plus 1 over 0 minus 2, which is negative 1/2. So the y-axis would be negative 1/2. So what we've got is we've got a graph that comes up like this, and then gets closer and closer and closer here. Now we need to know over on this side, is it above it or below it? So let's just pick in a number. Let's pick in 5. So we'd get 5 squared plus 1, that'd be 25 plus 1 is 26. Down on the bottom, we'd get 5 minus 2 is 3, which would be 8 2/3. So over at 5, 1, 2, 3, 4, 5, 6, 7, 8. So we're up here. So what we've got is our graph that looks like this. Now if we wanted to check that on our calculator, so we enter y equals x squared plus 1 divided by x minus 2. Let's do zoom 6 for our graph. So we get our graph that looks like this, which we've got, and it's got this one up here that we've got, so we're pretty good. Okay, you want to do one more? Let's look at this one real quick. This one's a little bit different. This one is not in reduced form. So what we do is we reduce it in that factor, so we get x plus 2. Okay, now because x minus 2 is in the denominator, and that is undefined if x equals 2, then what we do is we know that x can't be 2, so I'm going to put like that little vertical asymptote on here. But when we reduce it, we get x plus 2, so what we've got is y equals x plus 2. So that just means if x is 2, we don't have a value. This is linear. Okay, y-intercept is 2, so that's this point right here. Slope is 1, which means up 1, over 1, up 1. Well, it can't be on this line, so we're going to do an open circle. So what we've got is a line that just has a gap on 2. Okay, now you're ready to complete this section of homework on your My Math Lab.